Hello my dear students, the topic of discussion of this lecture is proving a result which will say us under which condition a given system of equations Ax equals to b you will have maximum number of basic feasible solution, and the maximum number of basic feasible solution for a system Ax equals to b where A is a matrix of order m by n is NCM that we have learned on the last lecture. After proving the result on existence of maximum number of basic feasible solution of a system of linear equations, we will move to have a geometrical look of basic feasible solution. For a given system of linear inequality, we will try to identify the basic feasible solutions and we will see exactly at which location of the given region the basic feasible solutions are lying. Fine, so these two are the agenda of this lecture. If we look back to our last lecture, the lecture number 2, we will find that we were discussing in the lecture number 2 the notion of basic feasible solution, and also we have talked about the notion of degenerate solution. If I just quickly have a look, at first the last lecture was started with giving a few examples of solving geometrically, solving graphically a two-dimensional linear programming problem. That is, when your problem is having two variables, then graphically we will be able to solve, and by solving them graphically we have found that there are five possible nature of the solutions of linear programming problems, and these are the five possibilities. And to identify these five possibilities before solving it graphically, or when your problem cannot be solved graphically, that means when your problem is having four or more number of variables, then in that case obviously the graphical solution approach will not work. In that case, before moving to solve a linear programming problem, can we be able to identify under certain condition, and under observing the values of the coefficients in the matrix capital A and capital B and the vector C in the objective function, can we be able to identify by looking at the values on A, B and C the nature of the solution a priori, and that will benefit us in the sense of at the mid of your solution you can just skip solving it by declaring that the solution is unbounded. Fine, or it doesn't have a solution, or it will have infinitely many solutions. So that will reduce our computational effort to just move at the end, and then you declare that well your problem is not having a solution. Instead of that, at the mid of your calculation, if you somehow be able to declare that this problem will have unbounded solution or any of these five natures, then that will benefit in the sense of we don't have to put some of our computational effort in vain. Fine, and towards this identifying mm, some expression involving the coefficients capital A, B and C for a linear programming problem, can we be able to declare a priori that well your problem will fall into any of these five categories? Fine, so that is our endeavor. We are moving towards that, and to move towards that we started our discussion in the topic of the notion of basic feasible solution, and the basic feasible solution was given by the system of given by this bxb plus nxnb is equal to b, where b is a matrix of order m by n which is a submatrix of the matrix A of order m by m, and this b is a non-singular matrix. Then you find the value of xb as b inverse b and put rest of the variables x and b's, those are all 0, and you will get a basic feasible solution, a basic solution. And if this solution xb satisfies the restriction that x greater than equals to 0, then we call the solution, this xb xnb, as a basic feasible solution. Because in the constraint of your linear programming problem, you just don't have this ax equals to b, but also you have x greater than equals to 0, and therefore if any point x that satisfies ax equals to bx greater than equals to 0 is called a feasible solution of this problem, a feasible point rather of this problem. And if your xb satisfies the feasibility restriction, that means xb satisfies ax equals to b together with x greater than equals to 0, then we call that solution as a basic feasible solution or a basic feasible point. Okay. Now, on the last day also we have identified in this note 2 that the maximum possible basic solution of a system of linear equations Ax equals to b is NCM. And also we have came across a particular notion that is called as the degenerate basic solution. If any of the component of B inverse B is obviously having m many components, right? B is a matrix of order m by m, and this small b, the right hand side of this x equals to b, is having m many components, and therefore B inverse B is obviously an m vector which is having m many components. If any of the components of B inverse B is equal to 0, then we call that solution as a degenerate basic solution. Fine. So these were the topics those we have described on the last day. Majorly we described on the last day the notion of basic feasible solution and degenerate basic solution. Now today we shall start our discussion with a particular result which will give us a necessary and sufficient condition satisfying which we can ensure that a given system of equations Ax equals to b will have maximum number of, that is NCM number of, basic non-degenerate solution. Here, unless otherwise specified, from this lecture and rest of the lectures, once we are writing Ax equals to b, we will mean that A is a matrix of order m by n. X has n many components, so X is belonging to the n-dimensional Euclidean space Rn, and B is a given vector in the m-dimensional Euclidean space. Fine. And we also will assume that the rank of the matrix A is equal to m. Together with this, we also assume that in this system, in the matrix A, m by n, this is a horizontal rectangular system. That means you have m is less than equals to n. We have described in detail why this m less than equal to n restriction will not lose any generality of this system of linear equations in terms of its solution. We have described it in detail, and therefore I'm not re-describing it, but let us now then we go for just handling this system of linear equations, which is a system of linear equations obviously has the restriction of a standard linear programming problem. A standard linear programming problem is the following form, that it is a maximization type problem. It is C transpose X, where C is a vector in the n-dimensional Euclidean space, subject to you have Ax is equal to B, where all the components of B are non-negative, and also you have all the components of X are non-negative. Fine. So this is we call as standard form of a linear programming problem, and in the standard form we are assuming here, which is eventually not losing any generality, that the matrix A is of order m by n, rank of A is m, and m is less than equal to n. We are under this assumption. Under this setup, we are going to describe several results. And here, several results on approaching to solve this standard linear programming problem. At first, we will now describe a very important result which says the following. which says a necessary and sufficient condition, or rather it is not a, the necessary and sufficient condition for the existence and non-degeneracy of all the basic solution, all the basic solutions of Ax equals to b is that every set of m columns of the augmented matrix augmented matrix that you all know for this system of linear equation is A, the matrix A, then side by side you write the matrix, the vector B. Of the augmented matrix AB is linearly independent. Fine. So what does this result says? This result says that if you find that every set of m columns of A and B, here you note that capital A, this matrix, is having precisely n many columns. Those are A1, A2, AN, right? Where each of AI is an M vector. Fine. By M vector we mean it has M many components. And therefore in this matrix AB you have how many column vectors? You have n plus 1 many vectors, right? Out of these n plus 1 many vectors you choose any of the m columns. Out of the n plus 1 columns you choose any of m columns. Then if you find that any of the m columns of this matrix is linearly independent, then this system Ax equals to b will have all possible basic solutions. That means we'll have maximum number of basic solutions, NCM number of basic solutions, and all of them will be not degenerate. That means none of the component of the basic variable values of your basic solution will be 0. Fine. That is what the meaning of this result. Let us now try to prove this result. For the forward part, for the forward part, it is if and only if result, right? So for the forward part, we assume that that every basic solution of Ax equals to b that exists and that is non-degenerate. Then we'll prove that every set of m columns of the augmented matrix is linearly independent. So start with let every basic solution and how many basic solutions you have? NCM many. Every basic solution of Ax equals to b is non-degenerate. Every basic solution exists and is non-degenerate. Fine. So let MCM basic solution exists of AX is equal to B, and every basic solution is non-degenerate. We are under this assumption. Fine. And then we will prove that every m columns of AB is linearly independent. Once you are assuming that there exists NCM basic solutions, so inside of this, obviously you have any m columns of the matrix capital A is linearly independent. Otherwise, you cannot have NCM number of basic solutions, right? So this implies then, therefore, every m columns of A is linearly independent. We need to prove that, we will show that, required to prove is that every m columns of the augmented matrix A side by side B is linearly independent. That is what we need to prove. How do we prove it? To prove it, we will do the following: that every m columns of A is linearly independent, right? And therefore, now you take any m columns of A, any m columns of A. Let us just, for simplicity, we and without loss of generality. So we consider let we you have the columns. You have m many columns. Those are A1, A2, AM, B, any m columns of A, column vectors distinct, they are distinct column vectors of the matrix A, and we will show that then with this m vector you just drop one vector and replace that vector by B, and that will be linearly independent. Fine. And if you can show that just by dropping the ith vector by B, the rest of the m vectors are linearly independent, then that will eventually prove that any m columns of the augmented matrix AB is linearly independent, right? Because here you have taken arbitrary m many column vectors of the matrix A, okay? And arbitrariness of this choice of m many distinct column vectors of A will prove that any column vectors of m many column vectors of augmented matrix AB is linearly independent. If you can prove that, you can replace any of the vectors out of this A1 to AM. You can replace by B, and rest of them by replacing AI vector by B. If the vectors m many vectors consisting B will be linearly independent, that will prove the result, right? So let us try to prove this result. Once you have taken these distinct columns of m many columns of the vector A, and therefore then this set consisting all these m many vectors is linearly independent, because they are just m columns of A, and you have assumed that there exist NCM basic solutions of Ax equals to B. Therefore any m columns of capital A will be linearly independent, and therefore this set is linearly independent. Can you notice that this A1, A2, AM, although I am just writing first m many column vectors, but you can just, if you are not choosing the first m many column vectors of the matrix A, then you just name the columns that you are choosing by A1, A2, AM, and accordingly you can go ahead with the proof. So not necessarily here inside of this writing A1, A2, AM, by that I am not necessarily meaning that only the first m columns of the matrix capital A you are choosing here. Any m columns of the matrix A you have chosen in this line A1, A2, AM. Fine. So here this is linearly independent. Then once they are linearly independent, then corresponding to this linearly independent solution, corresponding to this linearly independent set of columns, you construct the matrix B linearly independent, and hence you construct the matrix B given by A1 is the first column, A2, then AM. This matrix is non-singular submatrix of the matrix A. Fine. This is a non-singular m by m submatrix of the matrix A. Okay. Then corresponding to this capital B, you will have a basic feasible basic solution to the problem. So we let you have, let's suppose, P1, P2, PM, then rest of zeros, n minus m many zeros. Here this is the basic solution of the given system of Ax equals to B, and you are assuming that this is a basic solution, and once this is a basic solution, this basic solution is corresponding to B. By that I mean here you have n minus m many zeros, and this solution is obtained by taking the basic variables xb, then you take the construction xb as the basic variables, and x and b are the variables, are the components of xs which are not associated to the column vectors of b. Then let's suppose the matrix is bn or nxb equal to b, then you are putting this x and b is equal to 0. The way to find basic solution that I am describing here, and then by taking xb equals to b inverse b, you have obtained this solution, and that will be a basic solution indeed. And you have, under your assumption that every basic solution exists and they are non-degenerate, so none of these p1, p2, pm is 0, right? None of them. P2 is non-zero, Pm is also non-zero. Fine, because of your assumption that any basic solution is non-degenerate. Fine. And once you have this, then obviously you have the following. Then you have A1 P1 plus A2 P2 plus AM PM is equal to B, right? That is what I have written. This equation I have written. Bxb is equal to B. Fine. And here you notice that none of these pi I equal to 1 to m is 0, and therefore by the replacement theorem that you have learned in your mathematics 2, The replacement theorem, let me repeat once again, the replacement theorem. In the class, when in the lectures of mathematics 2, when you have to construct a basis of the n-dimensional Euclidean space, you have gone through the following result, which says the following. If, let's suppose, you have a1, a2, am is a basis of is a basis of the m-dimensional Euclidean space, and you are taking up a vector outside of this vector, outside of the linear span of this vector, or inside even you take, and let's suppose, and you take b is equal to, let's suppose, a1 b1 plus a2 p2 plus am pm. This, and you have any of the pi's, let's suppose pk is not 0, then you have shown in your mathematics 2 that the vectors a1, a2, ak minus 1, and you replace ak corresponding to this pk, for which you have pk is non-zero. Pk is a scalar which is non-zero, and if you are replacing the vector ak by the vector b, and then keep the rest of the vectors as they are, then this will construct a basis of Rm. Fine, this result you all have gone through in your mathematics 2, and the same result we will apply here. That here you notice that you have not only one pk, but all pk's, all pi's are not zero, and therefore since pi is not zero for every I is equal to 1 to m, what you can replace the ith vector by b, and still the vector a1, the set of vectors ai minus 1, ai plus 1, and in the place of ai you take the vector b, ai plus 1 am is a basis of the m-dimensional Euclidean space, and obviously this is linearly independent, because any basis is linearly independent and that spans the entire vector space Rm, and therefore it is linearly independent for all I is equal to 1 to till m. Okay, and therefore what you have proven, that for your chosen m many column vectors, which was arbitrarily chosen, for your chosen m many column vectors which is linearly independent set, you can replace any of the vector by the vector b, and if you replace any of the vector, let's suppose ith vector by b, and then the m many vectors consisting the vector b and deleting the vector ai is linearly independent. And as these m many vectors were arbitrarily chosen m many distinct columns of capital A, therefore you now have proven that any set of m many column vectors of the augmented matrix, arbitrariness of the choice of distinct columns of A proves that any m column, any m distinct columns of the augmented matrix A B is linearly independent, and this is by this line, by star. Fine. So we have proven the fact that if there exists NCM number of basic solutions of the system of equations x equals to b and all of them are non-degenerate, then any m columns of the augmented matrix AB is linearly independent. Fine. Now let us prove the reverse, that we are assuming that any set of m columns of the augmented matrix is linearly independent. Will prove that there exist NCM number of basic solutions and all of them are non-degenerate. So let us suppose, let any m columns of the augmented matrix is linearly independent. Fine. And now we will prove that there exist NCM number of basic solutions and all of them are non-degenerate. Once you have taken here that any m columns of AB is linearly independent, therefore any m columns of capital A is also linearly independent, because any m columns of capital A are also m columns of the augmented matrix AB, right? And therefore any m columns of the matrix A is linearly independent, and hence there exist NCM number of basic solutions, right? Now let us prove that all of the basic solutions are non-degenerate. Fine. And for that, so let us consider the equation. Let us consider the equation we consider the equation. You take any m columns a1 q1, any m columns a1 a2, then a3, so on, plus a m. So a1, you consider this linear combination a2 q2 a3 q3 am qm is equal to b. That means you are assuming that, let us suppose q1 q2 qm be a basic solution of ax is equal to b, and we consider the equation now, this equation. Now what do we have to prove? We have to prove that none of the components of q1 q2 qm is 0. If any of the component is 0, what will happen? If any of qi is equal to 0, so if let's suppose xk, sorry, let's suppose any of these m many components q1, q2, qm is linear is 0. So if let's suppose q kth component is equal to 0, then what will happen? Then you notice the following. If let's suppose qk is equal to 0, then you have a1 q1 plus a2 q2 plus ak minus 1 qk minus 1 plus ak qk is 0, and therefore ak qk will not be there. Ak plus 1 qk plus 1 plus end up with am qm minus b is equal to 0. And what does it prove? This shows that, which implies the set of m vectors, that a1, a2, a k minus 1, a k plus 1, a m, b is linearly dependent because you have here the coefficients of q1, q2, qk plus 1, qm, and the last coefficient is minus 1. So at least one non-zero coefficient you have here in the linear combination of these m many vectors equal to 0, and therefore this is linearly dependent. And once it is linearly dependent, you are violating your assumption that any m columns of the augmented matrix AB is linearly independent, which is contradictory to this star, which is contradictory, but this is contradictory to star, your assumption, right? And hence what will happen? None of this q1, q2, qm is 0. Hence none of q1, q2, qm is 0 for all I is equal to 1 to till m. Fine. And therefore you are then you have then proved that the solution, this basic solution, is non-degenerate, and it was any arbitrary basic solution you have taken. And then what you have? Hence, or arbitrariness of the choice of a basic solution, arbitrariness of this q1, q2 of the basic solution proves that, proves the result that none of the basic solutions of ax equals to b is degenerate, right? That is what you wanted to prove, and that completes the proof. Fine. So and here we must assume the following, that here You have taken that q1, q2, qm is a basic solution, and here hidden into it, obviously, we are meaning that the rest of the components are zero, and the column vectors associated to q1, q2, qm are a1, a2, am. So we assume that, let us suppose this, and and a1, a2, am are column vectors, columns corresponding to the components q1, q2, qm. Okay, and then we now consider the equation. We now consider the equation this. Then you go ahead. Fine. Well, so you have now then proven the following, the fact that the necessary and sufficient condition for the existence and non-degeneracy of the basic solutions, of all the basic solutions, is that every set of m columns of the augmented matrix is linearly independent. Fine. Now next we will try to have a look of a process how we go for finding basic feasible solutions of a given system of linear inequalities, and we will try to look at the positions of the basic feasible solutions, or rather let me go for only basic solutions for a system of linear inequalities. How do we go for that? Let us consider a particular problem, and with numeric values we will try to understand how do we process for finding the basic solutions. The example, find the basic solutions of the following system of linear inequalities. And the system of linear inequalities are following, that x1 minus 2x2 is less than equal to 2, and x1 plus 2x2 is less than equal to 4. Only this system of linear inequalities is given before us, and it is asked that find all the basic feasible solutions of the following system of linear inequalities. Then locate the basic solutions locate all the basic solutions in the region, in the geometrical region given by this inequality. In the geometric region, a geometric region, you graph out the region in the R2 plane of these inequalities. Geometric region given by let's suppose this system, let me name it as 1, given by 1. Fine. So let us go for it. At first let us try to find the basic feasible solutions. To find the basic feasible solution, we know that we have learned so far how to find basic feasible solutions or basic solutions of a system of linear equalities. Fine. And for linear inequalities, how do we go for it? You notice that corresponding to every linear inequality, you have a linear equality by adding slack or surplus variables, right? So corresponding to the first equality, if we incorporate the shortage of variable or the slack variable x3 here, so we will consider here x3 greater than equal to 0 and plus x3, and therefore it will be equal to 2. So by incorporating slack variables, slack variables x3 and x4, we obtain from 1, which is equivalent to from 1 that x1 minus 2x2 plus x3 is equal to 2, x1 plus 2x2 plus x4 is equal to 4. We should also have x3 greater than equal to 0, x4 greater than equal to 0. Fine. Now for this system, you know how to find the basic solutions, right? For this system looks like this system. Ax is equal to b together with x greater than equal to 0. So here the coefficient matrix of this system, the coefficient matrix, that is the matrix A, of this system is the matrix A, which is equal to, it is a 2 by 4 matrix. The first column is the column of the variable x1. So it is 1 1. Then you have minus 2 2, minus 2 2. Then you have 1 0. Then you have 0 1. Fine. This is your coefficient matrix. And the requirement vector, this B is called as requirement vector, as if when you are putting this x equals to b as the constraint of your linear programming problem. If I am writing a linear programming problem in the following manner, that maximize C transpose x subject to x equals to b, then this restriction x equals to b is thought of as if you are trying to meet the requirement. B is your requirement, and you wanted to meet that requirement. Satisfying that you have meted your requirement, you try to find the maximum value of your profit C transpose x, and this is called as profit function or the objective function which you wanted to maximize. Objective function is C transpose x. The matrix A is called the coefficient matrix of the system x equals to b. Fine. The coefficient matrix of this given system is A, capital A is this matrix 2 by 4 matrix, and the requirement vector, you may write or may not write this as requirement. You can just write B is equal to, and requirement vector B is equal to 2 4. Fine. Now let us now go for finding basic solutions of the system x equals to b. To find basic solutions of x equals to b, what is the process? The process to find basic solutions of x equals to b, let me repeat once more, although we have described on the last day, that at first you find the rank of the matrix capital A. Then if the rank is equal to m, then you go for finding a m by m submatrix. Let's suppose it is m. So if the rank of a is equal to m, then you take an m by m submatrix of the matrix A, which is non-singular, or you are choosing m many columns which are linearly independent of the matrix capital A. You choose m many columns of capital A which are linearly independent. With those m many linearly independent columns, you construct the matrix B. Fine. Associated to the column vectors of capital A, you define a vector of variables xb. Then you construct the system bxb, plus you take the rest of the vectors which are not in rest of the variables which are not in xb as xnb. Then you divide this matrix capital A by b and n columns. The columns of b and n will give us the complete matrix capital A, and therefore bxb and bxb plus n into xnb will give us the vector b, because this is your system x equals to b. You put xnb equal to 0, and then you have xb is equal to b inverse b, and these b inverse b together with xnb's are all 0 will constitute a basic solution of the system x equals to b. That is what the process is that we have described on the last lecture. Now here the rank of A is equal to 2. Let us now try to find set of all 2 by 2 submatrix of A which are linearly independent. Corresponding to every non-singular 2 by 2 submatrix of capital A, you will have a basic solution. Fine. Now let us try to find what are 2 by 2 submatrices of the matrix A. 2 by 2 because the rank of is 2. If rank is something other, let's suppose 1, then you will find 1 by 1 submatrix and so on. Fine. Because you have to have m by m submatrix, this is capital B. And here rank of A is equal to 2. Now the 2 by 2 submatrices of the matrix A are the following. 2 by 2 submatrices of this matrix are, how many 2 by 2 submatrices will you have from this matrix A? Obviously there will be 6. 4 choose 2. Fine. Out of these 4 columns, the ways you can choose 2 columns is 4c2. 4c2 is your 6, right? And therefore those are the matrix B1. You choose the first column with the second column, then B2 first column with the third column, B3 which is first column with fourth column, then we choose B4 as the second column with the first column is already taken here, B1, and then second column with the third column, B5 is second column with the fourth column, and the last matrix B6 is the third column with the fourth column. Fine. So these are 6 matrices. There are 4c2. 4 choose 2 many. 4 choose 2 because out of the 4 columns of A, the ways you can choose 2 many columns are NC2, right? Now, now let us check whether all of these are non-singular. And once any of them is non-singular, obviously at least one of them will be non-singular because the rank of the matrix A is equal to 2. Because here the B6 matrix, the determinant of B6 is equal to 1, which is non-zero, and therefore the rank of the matrix A is equal to 2. Rank of A is equal to 2 since it is better always to write here. Since the submatrix you take B6 1 0 0 1, which is a submatrix of A and which is non-zero. And now let us go for finding basic solutions. How many basic solutions are there? Here you can have at max 4C2, 6 many basic solutions. But maybe you may have the possibility that out of all these 6 matrices, 6 submatrices, you may have one or two or many of them are singular. If any of them is singular corresponding to that submatrix Bi, you will not have a basic solution. Fine. So let us now check one after another which one is non-singular, and corresponding to that let us try to find the basic solution. So let us start with B1, and the determinant of B1 is how much? We are checking for non-singularity. It is 2 plus 2, which is 4, and non-singular 0. And then once it is non-singular, then we go for finding the basic solution corresponding to capital B1. How do we find the basic solution? So we have to construct at first the variable vector xb1 corresponding to b1. What are associated to b1? You try to find out the column vectors of A. Column vectors of b1 are the first and second column. Associated to the columns of A, you find the variable in the given system. Corresponding to the first and the second column, the associated variables are x1 and x2. So your xb1 is equal to x1 and x2, and your then xnb1 not associated to b1 are your x3 x4. You have to put this xnb1 is equal to 0. You put it 0, and you also have to find the matrix which is no column vector, which are rest of the column vectors of A which are not in b1, and therefore in n you will have the matrix 0 1. Fine. Now you take up the equation, consider the equation ax equals to b. Ax equals to b will give you x equals to b, and x equals to b will imply now x equals to b, we can write it as b into xb1, b1 into xb1 plus n into x n b. Fine. And this is equal to b, and you now consider this with x n b1 is equal to 0, and it will give you then x b1 is equal to b1 inverse, and this will now b1 inverse. B1 inverse is here, the determinant is 4, so 1/4 of the inverse that you all know. You have to interchange these 2 and 1, and you have to multiply by negative the another diagonal 2 minus 1. This is your inverse of b1 times b. What is small b? Small b is your 2 4. Fine. 2 4. Let us just simplify it. You have 1/4 of 4 plus 8, 12, minus 2 4, so it is 2. So therefore we have 3 and half. And therefore the basic solution corresponding to b1 It is not only basic, it is also basic feasible, because all the components are greater than equal to 0. Therefore, the basic solution corresponding to B1 is, what is that basic solution? You have the x1 is 3, x2 is half, x3 is here, x3 is here, x3 you have taken 0 and 0. So you are setting the non-basic variables. These variables are called as basic variables. The variables which are associated to the basic columns, that means to the columns of B1, are called basic variables, and the variables which are not associated to the columns of B1, they are called non-basic variables. So the basic variables are x1, x2, non-basic variables are x3 and x4. Fine. And therefore the basic solution corresponding to B1 is this solution 3 half 0 0. Now let me go for calculating another B2. Next is B2. The determinant of B2 is equal to 1 minus 1. So it is minus 1, which is not 0, therefore it is non-singular, and therefore we will have a basic solution corresponding to capital B2. Corresponding to capital B2, what are the variables? So basic variables corresponding to B2 are corresponding to B2. B2 are which columns? Here is your first and third. Therefore x1 and x3. xB2 is x1 and x3. These are basic variables, and non-basic variables are in B2 are x2, x4. Rest of the variables which are not basic. And the matrix N, let us name here by, if I am writing by N1 B1, then I am writing here N1. So it is N1. And N2, let me write here. N2 is the column vectors which are not in B2. Not in B2 are A1 and A4. So 1 1 0 1. 1 1 no. You have first and third. Therefore second and fourth. Minus 2 0 1. Minus 2 0 1. Okay. And now consider Ax equals to B with x in B2 is equal to 0 0. So you are setting x2 and x4 0, and then this Ax equals to B will give us, which gives B2 x B2 is equal to B, or it gives us x B2 is equal to B2 inverse into B. B2 inverse is how much? What is the matrix? B2. B2 is the matrix 1 0 0 1. So 0 and 1 will be interchanged, minus 1 minus 1. So 0 1 0 1 minus 1 minus 1 divided by the determinant 1 divided by minus 1 into 2 4. Fine. And this will now give us minus 1 into, you have minus 4, so minus 1 minus 4 is 4, minus 2, so 4 2. Fine. And therefore the basic solution corresponding to B2 is, you have x1 value, x1 is 4, x x3 is 2, x2 is 0, so this vector, fine. So this is the basic solution corresponding to xb2. Here again all the components are non-negative, and therefore this is also a basic feasible solution. But it is not asked to us to find basic feasible solution. If it is asked to find basic feasible solutions, then after finding the basic solution, you check whether the components, all of the components are not zero, or all the components are non-negative or not. Fine. If non-negative all the components are, then that basic solution will be basic feasible solution. Fine. Now here I am not then going for calculating for all of the others. So I am just giving you the solutions, and the basic solution corresponding to B3, B4 and B4, B5 and B6. You please verify all of them corresponding to B3. The basic solution is corresponding to B4. The basic solution is corresponding to B5. The basic solution is corresponding to B6. The basic solution is. So one after another, let me take up corresponding to what is B3. B3 is 1011. B3 is 1011. Let me try to find for 1011. For B3 this solution, and rest of them also I have written here what are the solutions, you all can verify. And by transpose I mean these are all column vectors with four many components. Here, okay, I guess I have done a mistake here. The calculation, here we have -1, then -2, this is 4, and then -2. I have here, I should have -2 here. Sorry, this will be -2. This will be -2. Okay, so these are your all 6 basic solutions I have now collected. Then it was asked that you locate those basic solutions in the geometric region given by 1. So let us try to graph out the region given by these inequalities. So the inequalities, let me just quickly write them down. The inequalities are the geometric region of the inequalities x1 minus 2x2 less than equals to 2, and x1 plus 2x2 is less than equal to 4. This is, let me draw, where we will have this is our x1 axis, this is our x2 axis, then x1 by 2, x2 by -1. So x2 by -1 is here, say here is 1, x1 by 2. Fine. So here this line this line is your x1 minus 2x2 is equal to 2, x1 minus 2x2 is equal to 2, and which side less than equal to 0, less than equal to 2. So yeah, origin side, because origin is satisfying this inequality, so this side. And x1 by 4, x2 by 2, x2 by 2 is here, x1 by 4, let me suppose here. Then the line will be given by the line will straight away go to this, fine, this line. And which side? The side of 0 0 0 0 will satisfy this, so this side, and therefore this is the inequality. So this region, and in this inequality region you don't have any restriction of x1 or x2 greater than equals to zeros, and therefore you have this entire region, fine. And let us try to find out what are the locations of basic solutions. Here this point of intersection is the point, you can find it, this is the point 3.5, and this is the point x1 by 2, so it is 2 0, and this point is your x2 by 2, so this line is x1 plus 2x2 is equal to 4, and this line is 0 2, fine. Let us now try to look at what are the locations of all the basic solutions. For the first, the basic solution here, it is your 3 is your x1, half is your x2, 0 is x3, and 0 is x4, fine. And therefore x1 x2 is equal to, in the plane of x1 x2 you have this point 3 half. So if I am denoting it by the notation, let me suppose this is the notation, the basic solution, let's suppose it is a1, okay, and then a1 is the location 3 half, fine. Then let us look at the next basic solution, which is 4 minus 2, 4. So in the x1 x2 plane it is 4 0, 4 0. Is there any point where you have 4 0? 4 0 is this point, 4 0. This is your a2, fine. And then so we are denoting it by a2. Then you have in the x1 x2 plane it is 2 0, right? This is 2 0, a3. So here is the location a3, a3 is here. Then you have 0 2, 0 2 in the x1 x2 plane, this is your a4, a4 is 0 2, this is your a4. Then a5 is 0 minus 1, a5 is 0 minus 1, this point 0 minus 1 is a5, and a6 is 0 0, this point a6. So these are your basic solutions, but you notice the following. Let us reanalyze the basic solutions. You notice that the given system of inequalities were this, right? So any solution that you wanted to find for this system must be a solution of this equivalent system, where x3 and x4 must be equal to, here x3 and x4 must be greater than equal to 0, fine. So wherever you don't have x3 greater than equal to 0, those are not solution of this entire system. Although we have found basic solution for ax equals to b, not for entire this system, but we have to find for the system 1, right? We have found basic solution for this only ax equals to b. We have violated, we have discarded this x3 greater than equal to 0 and x4 greater than equal to 0. We have not considered this into account while calculating the basic solutions. So wherever x3 and x4 are not greater than equal to 0, those solutions are to be discarded. For instance, this solution has to be discarded. This is not a basic solution of 1, which is not a basic solution of 1 because which is not a solution of 1 because you have x3 is less than 0, right? And therefore a2 has to be discarded. Is there any other which has to be discarded? Is there any other point which has to be discarded? No other point, right? All other components with x3 x4 are greater than equals to 0, so a2 has to be deleted. So we don't take into account the point a2. We'll let them, we are rubbing it, is a2. a2 is not to be taken into account for the given inequality region. Fine. So you have then rest of the points a1, a1, a3, a4, a5 and a6. So these points are to be taken into account. The location of a6 is over here. Fine. Okay. And now if we go for the system, so these are your locations according to the problem that was asked here. The problem is solved that all the a1 a3 a4 a5 a6 are your basic solution of the given system, and those have been located, all these 5 points have been located in this feasible region. Fine. And they are all the feasible region that you all can see here. Now we put a note here, very special note. The note is the following: if we consider these two inequalities as constraint in a standard linear programming problem, then we also have to have x, all x, so I is greater than equal to 0, and therefore for the region, if we take into account these two inequalities together with the non-negativity restriction x1 plus 2x2 less than equal to 4 with x1 non-negative, x2 non-negative, for the region, for this region, the basic feasible solutions. What are your basic feasible solutions? Are basic feasible solutions of this system: x1 minus 2x2 plus x3 is equal to 2, x1 plus 2x2 plus x4 is equal to 4, together with all the variables non-negative x1, x2, x3, x4. Fine. Now, can we be able to identify the basic feasible solution from the earlier calculation, from the calculation of this? You note that in the calculation of this problem, we have found basic solutions of this ax equals to p. We have not taken care of the non-negativity restriction, and therefore for with the non-negative restrictions, the basic feasible solution will be can be filtered out from the basic solution of this system of equalities from the first two equations, right? So if you filter out, then the basic solutions will be given by we find out the points which are satisfying all the basic solution of this problem, which are satisfying the condition that all the components of the solution are all the four components of the solution are non-negative. So A1 is a point, A2 is not, A3 is, A4, A5 is not, and A6. Fine. So if we now try to find out the points, the basic feasible solution of this that is the points which are your A1 is, then A2 is not, A3, A4, A6, A3, A4, A6, fine. And therefore, where are the location of these points in the feasible set, in this feasible set, where all the variables are restricted by non-negativity restriction, is that here we'll just quickly draw it out. Here this region will be this kind region. Here is one. So here are the locations. A1 from this figure. A1 is here. A3, A6, A4. A1, A3, A4, A6. Fine. And we will prove next is the following. Before that, let me tell you one thing here. That you notice that precisely the basic feasible solutions are the vertices of the polygonal region that is given by the inequalities or given by ax equals to b. Here is your ax equals to b, and together with, if you take the restriction x greater than equal to 0, then for this set, that is the feasible set of a standard linear programming problem, the basic feasible solution of this system are precisely the of vertices of the geometric region given by these two inequalities. Fine, and we'll now slowly move towards proving this fact that the basic feasible solutions of this constraint set of the standard linear programming problem are precisely the vertices or the extreme points of the geometric region given by the inequalities x equals to b and x greater than equals to 0. And here I have said a very special terminology. I have said vertex or an extreme point. Now, how do we mathematically present the vertices? How do we say some points are vertices or extreme point of a given geometric region? So we have to now study a bit about convexity and geometry of convex sets. And there we will find that the notion of extreme points will be precisely these vertices of an in-polygonal region. Fine. So in the next day then we will start our discussion in the topic of convex set, convex regions, and then few special terminologies depending on convex sets which are required in the development of the method, the simplex method, to solve a standard linear programming problem. Fine. So on the next day, the agenda, the topic of discussion is convex sets. Fine. Convex sets in obviously n-dimensional Euclidean space. That will be the topic of discussion in the next lecture. Thank you. Thank you all for all of your kind attention.